Welcome back, Lecture 24, Calc 1, Math 141. We are just about finished with the chain rule. We can entertain some questions about the chain rule today. Hopefully we'll have more time for that. We ran out of time yesterday in the last tape lecture talking about a homework problem, and I did email the students that are in this class, but I also realized that this is going out on cable TV and it will be used in future semesters for this course on DVD, and I'm probably not going to email them. So let me briefly address what it was that I sent out in the email. And I didn't finish it in the email either, so we might want to take a look at what we think happens and then what we can justify happens. So yesterday, at the end of class, we took a look at this situation. I've redrawn the diagram so it won't be so cluttered. But we want to talk about the area of the semicircle, that's in the numerator right here, compared to the area of the triangle as you take this angle and condense it. Okay, basically push the two sides of the isosceles triangle together and cause angle theta, this entire angle, to get smaller and smaller and smaller. Well, clearly, as you do that, the area of the triangle gets smaller and the area of the semicircle gets smaller. That doesn't necessarily mean that the answer is 0. They could be decreasing in such a way that this area is always 1/4 of this area, or this area is always 7/10 of this area. So you really don't necessarily know that the answer is 0 because they're both going to 0. And when two things go to 0 in fraction form, that could be a lot of different answers. So it does turn out that the answer is 0, but I think we probably ought to get it to a point where we're all believing legitimately that the answer is 0. We can back it up. It's probably I would not consider this problem to be right down the middle of the road. This would be somewhere on the shoulder of the road, or possibly some of you might vote for the fact that it's in the ditch off the road. But it's not a test type question. It's not so-called what I consider fair test question or right down the middle of the road type question. So we want the area of the semicircle in terms of theta, could be trig functions, probably is trig functions, and the area of this b of theta, the triangle, in terms of trig functions as well. So that page is kind of cluttered. Let me bring this one in. So I think this is what we named yesterday. We did name that point M, and I think everything else is labeled appropriately. This P to M is the radius. M to Q is also the radius. That might come in handy. I don't think we necessarily called it that yesterday, but let's simplify it. This distance from M to R would be the height of this triangle. So if we could do base times height, multiply it by 1/2, we'd have the area of that. All right, for the area of the semicircle, we know that it's going to be half the area of the circle. So the area of the circle is pi times the radius squared. That much of this, I think, is fair for a test. So there's some parts of this that are fair, but the problem as a whole is probably too lengthy and not necessarily fair for a test. So 1/2 pi times the radius, we need something to plug in for the radius, and then we'll square it. So we'll get a diagram off to the side and figure out what. For the area of this triangle, that would be 1/2 the base. The base is really what? 2r? Is that correct? Times the height, which I'll just leave as h. So 1/2 of 2 leaves us with r times h. So we need to know what r is. Let's figure out what that is in terms of theta, and we need to know what h is in terms of theta. So we need r, and we also need h. So let's use this triangle, this right triangle, right here to figure out what r is. And what h is, and let's have a segment in common. Let's use segment PR. So what would be a trigonometric identity that would have r in it and PR in it and half theta? Sine?
Theta equals radius over
And
r.
part of the problem in writing an email, and I apologize for having to write out the word theta in an email, but there isn't a symbol for theta. So if it is a Greek letter, I'll just have to spell it out. Sine of half theta would be opposite r over hypotenuse PR. And if we wanted to solve that for r, then r would equal what?
PR sine of 1/2.
So we can plug that in up here. PR times sine of 1/2 theta. That's the radius, so we plugged it in there, and we're going to square it. Down here we also have the radius. So we'll plug it in there for r. Now we need h. It's probably going to get a little too cluttered here. Let's see, I'd like to keep all this up here. What's a trigonometric identity that has h and PR and half theta in it? Cosine. Cosine of half theta would be adjacent, h, over hypotenuse, PR. And solving for h, sorry, getting a little cluttered here, PR, cosine half theta. So we'll put that in here. So we want to take this. That goes in the numerator. And we want to take this and put it in the denominator and take the limit as theta approaches 0. Everybody okay with that? It's getting kind of cluttered. We need to switch the page. By the way, theta approaching 0, isn't it true if theta is approaching 0, half theta is also approaching 0? And that we have the angle now in terms of, instead of theta, we have half theta. So I'm just going to put half theta approaches 0. All right, in the numerator, we have half pi. We have PR squared. And we have sine of half theta squared. Denominator, we have PR, sine of half theta, PR cosine of half theta. All right, so what knocks out?
PR squared.
Okay, PR squared with each of these down here, so they're gone. One of these sine of half thetas knocks out with that one. So we have, can I just factor that half pi out in front?
Yeah.
It's unaffected by theta, right? There's no theta in it. So half pi looks like that's gone. Now that's out in front. Sine of half theta over cosine of half theta. Now, when you get to this part in the problem, I think it kind of picks up with it being a fair problem once again. What's sine of half theta over cosine of half theta?
0.
Isn't that tangent half theta?
Yes.
So now we have a single function of theta what happens to the tangent of an angle as that angle approaches 0? It approaches 0, right? As the angle approaches 0, the tangent function approaches 0. Tangent function looks like this. So if you come in from this direction, it approaches 0. And we're not coming in from that direction, but if we were, it also approaches 0. So we end up with 1/2 pi times 0, which is 0. So some of you were conceptually thinking that if the theta got squeezed down to 0, they're both diminishing. That's true, but we don't know what their ratio is as they're diminishing. So now we know that apparently, well, you explain it to me. The fact that we got 0 for an answer, tell me what happens in this picture as the angle, this angle, right here, this entire angle, which is theta, as it compresses or condenses down to 0, the fact that we got 0 for an answer to this, explain that. Katie.
It means that the area of the semicircle decreased faster than the area of the triangle did.
Everybody hear that?
Yes.
That's what it means, that this area diminishes, apparently, because we got an answer of 0 at a rate that's faster than the area of the triangle is diminishing. Otherwise, we wouldn't get 0. So the numerator gets smaller faster than the denominator. So how many of you got 0 on that one and plugged that in? Okay. Any other pending questions from WebAssign or any content item, chain rule, content item
Yeah, I think I have
that
a
needs to be
question on one of
clarified?
the homeworks for the next homework. The f of x equals 5 secant 5x, and differentiate that.
5 secant
Yes.
of 5x?
Yes.
And the question is just to find the derivative?
Differentiate.
Okay. So you're going to have a variety of questions. Still, just the answer is just to find the derivative. And now they're going to have more and more questions where you find the derivative and then you use it a little bit, like find the slope of the tangent at a certain x value, find the equation of the tangent line. So you'll see more and more of those creep into the homework problems. So we want the derivative. This 5 is just a coefficient, so it comes along for the ride. What we want to differentiate is the secant of something. What's the derivative of the secant of something? Secant of that same thing, tangent of that same thing. But we don't just have the secant of x, we have the secant of 5x, so you kind of keep working your way in until we get to the innermost function, which is 5x. So the derivative of the secant of 5x is secant 5x tangent 5x times what? Derivative of 5x, which is 5. So isn't secant kind of the outside function, right? So we took the derivative of the secant here, and then 5x is the inside function. We took the derivative of that last. So
So
you
that
keep
wouldn't
working
be-
your way inside.
That wouldn't be like a multiplication or not a product rule, would it?
No.
Okay.
No, it's not a product rule because this doesn't have a variable in it. That's just a lead coefficient.
Okay. Okay.
And that's the only variable expression in this problem. So you can multiply the 5s together. You don't have to, but go ahead, Chandler.
So, well, the next one is like e to the negative 4x. So because that has a variable in it, it would be a product rule. What? Oh, I'm sorry. E to the negative 4x times cosine 3x.
Yes.
And so that would be product.
Right.
Okay.
If each term of the product, if both of them have variables in them, then that's a product rule.
Okay.
And you could use the product rule here. I mean, you'd get the same answer, but when you took the derivative of 5 with respect to x, you'd get 0. So the half of the product rule stuff is going to drop out anyway. So you'll never go wrong by using the product rule, but you'll work a little bit harder than you need to in some problems if you use the product rule. Anything else from either the WebAssign that was due yesterday or the one that's due Monday? I think it's due Monday. Is that right? Catherine?
one that was due last night, there was a question and it wanted you to like find equilibrium, but I didn't like. How do you find equilibrium?
Equilibrium, if it's the problem I'm thinking about, is it gave you the position.
Right.
And
You
it
had
was,
the velocity.
I think it was something that was oscillating.
It was negative 2 cosine x minus 3 sine x.
Okay, and that was the position.
Mm-hmm.
Negative 2.
Cosine x minus 3 sine x.
So that's an oscillatory function. Where is it at 0? Let's see. 0, this is at negative 2. Is that right?
Yeah.
So we've got this thing that comes up here, and then as time passes, it's oscillating back and forth. Okay. We'll look at things like this later in this course, and if something continues to oscillate, it's realistically, I mean, we would think, let's say a spring, and you release a spring with a weight on it, you would eventually think that the spring, because of friction, that these would diminish, right? That it kind of it goes back and forth, but eventually gets closer and closer to the axis here. They want to know equilibrium is right here, when it kind of goes through that position here or here or here. That's what they're searching for.
You just set it equal to 0.
Yes, you want S of t equal to 0.
So the original problem,
Yes.
not the velocity, not the acceleration.
That's correct.
Equal to 0.
So I think that was question A. Is that
Yeah,
right?
That was C.
That was C.
Yeah,
You had to find
first
the
derivative
velocity
of
and the
velocity.
acceleration.
All right, so tell me what question A was.
It was find the velocity at time t.
Okay, so first derivative,
Yeah.
stop, right? Okay, what's the part B?
It was
Find the
second
acceleration at
derivative.
time t.
Okay, so find acceleration, second derivative, all right. And then C was equilibrium, when it reaches equilibrium.
When does the
First
mass
time.
pass
The
through
first time.
equilibrium for the first time?
So we want the first time that is equal to, how do you go about solving that? How did you solve that?
Use a calculator.
Use a
Move it on the
Graph set to 0.
All right, so we want to know when negative 2 cosine of x minus 3 sine of x is equal to 0, right? So even if you use a calculator, you probably weren't able to plug this equation into your calculator. Oh, you graphed it? And saw where it was 0? Okay.
Yeah.
But let's say that we had an energy conservation quiz in here, and we did not allow calculators.
Well, that would
Would you be able to function
No.
without a
No.
calculator, Jonathan?
Yeah.
You can solve that equation, put cosine underneath sine, eventually and get it to tangent.
Okay, let's do that. Let's move one of these to the other side. So let's say negative 3 sine of x equals what? 2 cosine
in a
x?
solar power.
Yeah.
Okay, and if I want to divide both sides by cosine, you have to be careful because cosine can be 0, right? So we might either be deleting solutions or introducing solutions. But let's see if we can get away with that. So that will leave me sine over cosine, which is fine. But I don't want the negative 3 there. Divide by negative 3. And get rid of that. So sine over cosine, which is tangent, negative 2/3. Now, we could reintroduce energy into the problem and use a calculator, right? And solve for, instead of reading a graph, I take it that if you entered this in, you were reading a graph, right?
Yeah.
Where the graph took on the value 0. At least now we were solving an equation. This would be what? Inverse tangent of negative 2/3, right? Now I'm wondering if that's going to give you the answer, though, that you want.
It does.
It
After
Right. It probably, your calculator is programmed that it's going to give you the single value, the angle, the one value that has negative 2/3 for its tangent, but it's going to choose it from negative pi over 2 to pi over 2, so it's going to choose the negative one. So you have to say, well, that'd be negative time. When is the next time it would be at that place, right? So your calculator would actually give you what? Let's go ahead and kind of understand what our calculator is giving us and why it's not the appropriate answer for this problem.
Negative 0.588.
What is it?
Negative 0.588.
Negative 0.588.
Yeah.
So that's the angle, that's radians. Well, we didn't start this thing till time 0, so we want to know from time 0, well, this is the tangent function. When is the next time we could take the tangent of something and get this same value? What would we do to this? Add pi to it. The period of the tangent is pi, so the solution that we want would be negative 0.588 plus 1, right? Because we want the next time. And somebody tell me what that is.
2.55.
2.55?
4, yeah.
And I think I remember that answer as being correct. So don't always trust your calculator on a problem like this to give you what you need, but it'll give you enough to figure out what you need. Okay, anything else pending? Either yesterday's WebAssign or the one that's due Monday. Yes.
I'm not having trouble getting any of the answers, but I'm having trouble finding the right way to plug them in.
Yeah.
Okay.
Could you just go over to like how do you write down like when you have like multiple secants and tangents and all that?
Yeah.
Like how would you write it in a form that WebAssign will accept it?
Okay. Let me cover a couple things that some people have asked me about over the last couple days.
Okay.
If we have a problem that we would typically write down as e to the 4x, or if we were typing it in an email, we might write it as e caret 4x, right? WebAssign's not going to take any of those.
Yeah.
E is the exponential function, so you'd have to use exp 4x. So I think you've probably battled that a little bit in this course, but just remember it doesn't understand what this means. We've got to call it that. The other thing that you got to be careful about is we typically write down the sine of 3x. You have to put parentheses around that, right, for WebAssign. And sometimes we can write down 5 tangent of x, and there's an understood multiplication here. This is might be a little overkill, but if it's kicking it out as the fact that it doesn't like the syntax, go ahead and things that are multiplied, go ahead and put that star in there and clarify what are the things that are being multiplied. It's this thing times this thing. Yeah. But I sometimes will do it in both just to make sure that it's understanding. So what, do you have another specific situation?
When x is by itself with that tangent, do you still have to put in parentheses or
Yes.
accept
Yes.
tangent?
Sorry, I should have done that. Any trig function is going to want that angle, whatever it is, x, 5x, theta, 2 theta minus pi over 6. It wants it in parentheses.
If you have like a secant squared, you would just do secant of x and then the whole thing squared, like caret 2.
Yeah.
Because you know, like if you wrote it like in here, you could just write secant squared of x.
No, that's true. It also does not like that.
Yeah, that.
So if you had secant squared of x,
Yeah.
it doesn't know what that means. So you're going to have to write that out as secant of x
Parentheses around everything squared.
squared. We having a power crisis over here? I mean, I wasn't serious when I said we were having an energy conservation quiz or anything.
Living on wasting now.
Yeah. Okay, anything else? Yeah.
Like, let's say you're taking like you take sine of x, it would be cosine of x. What if it instead of x was a constant, like sine of 2, and I wanted the derivative of that? Would that still be 0?
That would be 0.
It would?
Yeah.
Because
Yeah, it's got to be, and that's a good point to bring up, is that these things, if you're going to derive them, they've got to have variables in them. If they don't, they're constants. So what Kent just said, there's a big difference between the sine of x and the sine of pi over 2. Well, the sine of pi over 2 happens to be what? 1. And what's the derivative of 1? Is 0. So there, that's a constant, nothing variable about that at all. Here, this is a variable expression, so we can find the slope of it at an instant, but it's going to vary as well. In fact, let's do, I don't know that we've done this, just so we can see a pattern here. Derivative of sine is cosine. If we continue with that, now what's going to happen? Now it's going to start all over again, right? So we have this cycle of sine and cosine, negative cosine. Fourth derivative would be back to sine, right? So in groups of 4, this kind of blocks of 4, it begins to repeat itself. And that's not true with the other functions, right? Just with sine and cosine.
Mm-hmm.
Anything else that's pending? Okay, as I mentioned before we started, it'll make next week a lot easier if we begin implicit differentiation today. So we'll have about 15 or 20 minutes to spend on that. And that's good because we're not going to be able to, we wouldn't be able to do all of this in one day anyway. So, and you guys know the reward for getting started with this today. Leonard, I'm going to switch to that one. If that's all right. So this is section 6, chapter 3. It's called implicit differentiation.
36.
It's very convenient that it follows right after the chain rule. And if you have any difficulty at all with this, think of this as nothing more than a chain rule problem. So in this fashion, if we have let's say this little squiggly line has some variables in it, and I don't want to specify what it is, but let's say we have that mass of letters and numbers in there. That whole thing is cubed. So in the chain rule, we knew to kind of use the extended power rule approach or the outside function, inside function approach. The outside function here is cubing function. So we would take 3 times this same inside stuff to 1 degree less. So it really doesn't matter at this point what is inside the letters and numbers until now, right? Because the last thing we have to do is take the derivative of that inside stuff, whatever it happens to be. That's chain rule, right? Everybody feels comfortable with that? Mm-hmm. I'm going to let's say that we know what's inside that thing, that mass of letters and numbers that's being raised to the 3rd power. And in fact, let's say that it is QRS, all kinds of numbers and letters. Okay? Numbers, we're always dealing with numbers. So we would say derivative is 3 So we're still at some point in time, regardless of what's there, we're going to get to a point where we have to take the derivative of whatever it is that's inside. So we're going to have either a way to find that derivative or a way to write it down because we really don't know what it is. So let's say that we want to take the derivative of, let me start with a simple example. we've got this equation. Not very complicated. It's got an x in it and a y in it. And they're going to get a whole lot uglier than this, but this is a good one to start with. What does that look like, by the way? xy equals 8. Give me some points on it.
0.
4 2's on there, right? 2 4, 1 8, 8 1, negative 1, negative 8.
Yeah.
Just take an x value and a y value such that their product is 8, right?
Okay.
So if we were to sketch it, 4 2 and 2 4, 1 8, 8 1, it's going to look something like this. And the negatives over here too. Now that looks like it hits the axis. That's because I'm not very good with this yet. It should be asymptotic to the axis right here. So that's roughly what this thing looks like. Now we could, in this equation, we could solve for y. Y would be 8 over x, which is equal to 8 x to the negative first. And we could find dy over dx. Why? Because we have y in terms of x. So since we have y in terms of x, what is the derivative of 8x to the negative first?
Negative 8 over x squared.
Good. Negative 8 x to the negative second, which is negative 8 over x squared. Now, does that make sense as a derivative if the graph is shaped like this?
Yeah.
Because slopes should all be negative, which they are. That negative 8 is, there's nothing variable about that. That's always negative. X squared is always positive. So any of these slopes that we identify here, that slope's negative, that slope's negative, that slope's negative, all of them negatively sloped. So it seems to fit. But we were able to solve that for y. Let's take that equation, xy equals 8, and let's just leave stuff where it is. Because sometimes it's not going to be convenient or even necessarily possible to solve for y in terms of x. We have a method. It's called implicit differentiation. Let's just differentiate things where they are. If they're variables, that's a variable. That's a variable. So we'll treat them as variables. And in fact, that's the product of two variable quantities. So we'll use the product rule. And the word implicit, not necessarily the case with this one because it is a function, but a lot of times you've got x's and y's and numbers all tied up in an equation, and the whole thing is not a function, but there are several functions kind of embedded within that or implicitly defined or described in that. So that's where the word implicit is coming in, is that chances are it might not be a function, but there are some functions implicitly described in that interrelationship. So if we were to use the product rule, we would say first times derivative of the second plus second times derivative of the first. Is that okay for the left side? And what about the right side? 0, right? Derivative of 8 is 0. Now let me add a little bit to this. That's typically what we have written down or at least thought through. Aren't we wanting to know eventually dy over dx? Right?
Yes.
That's where we're headed. We want y prime or f prime of x. So when we say dy, we really want the derivative of y with respect to x. We're deriving this whole problem with respect to x because of the fact that we want that. So when we derive x, we're deriving x with respect to x. So every derivative that we come across, we want to derive it with respect to x. I'm going to start on the second term because we know what it is. Y And what is the derivative of x with respect to x?
1.
That's 1. And doesn't it look like 1, right? If you derive x with respect to x, you get basically dx over dx, which is 1. That's the easier one. The first one, what is, and this is a self-answering question. I'm going to answer the question with the way I ask it. What is the derivative of y with respect to x? I just answered my own question. It's dy over dx, right? Derivative of y with respect to x is derivative of y with respect to x. So this is dy over dx. If it helps you to think of the fact that we're trying to derive a non-x thing with respect to x, that's exactly what we're doing. Here, we're deriving an x thing with respect to x. We know how to do that. We just write down what the answer is. Here, we're deriving a non-x thing with respect to x, so we basically just write down what it is we're trying to derive with respect to x. We're trying to derive y with respect to x. What do you think would be the goal from this point in this problem?
Solve for dy dx.
Solve for dy over dx, because that's what we want. So we've got x dy over dx equals what? Negative y. Divide both sides by x. How is that derivative different from any other derivative that we've come up with thus far in this class? It has a y in it. And what do we typically do with derivatives when we're done with them? What are some of the different things we've done? We've plugged in a point, like they'll give us a point. What's the, let's take a point on this curve. 4, 2, right, is a point on this curve. What's the derivative at the point 4, 2? Well, typically, we had our answer only in terms of x, and we plug in 4, right? Now, we have an answer in terms of y and x, so we plug in both coordinates of the point. So if we wanted to know the slope of the tangent at the point 4, 2, what would that be? Negative the y value over the x value. Is that right?
Yes.
Negative 1/2. So if we were to come back to our graph, is that on this page? No. It's not. Let's. So here's our point 4, 2. 2, 4. Okay, and we've got the other portion of the graph down here, but we don't care about that necessarily right now because we're concerned about what's the slope of the tangent at the point 4, 2. So we got dy over dx to be what? Negative 2 over 4. Is that what we just had? Right? Negative 1/2. Does that look like the slope of the tangent could be negative 1/2?
Yes.
Kind of a rough graph, but looks like possibly that line. Let's use our imagination that that's actually a line. That the slope of that line could be negative 1/2. Now, we did the derivative another way, didn't we? Didn't we get y prime? We solved for y in terms of x, and we took the derivative. What was that answer? Negative 8 over x.
Yeah,
Squared.
At that point, 4, 2, we better get the same answer, or I've made some mistakes and you let me get away with it. If we take negative 8 over the square of the x value, the x value is 4.
16.
Same answer, right? So it's going to give you kind of have to trust that process, that it's going to give you what you want. It's going to be in a different form. One of them will be in terms, if you can solve it for y in terms of x, that's wonderful. We have a whole bunch of rules then that we can use. If you cannot, or you just simply don't want to, it's fine. Just take everything all together. Any variable quantity has to be treated as such and differentiated as is. Any question on this example, this simple example? All right, let's go to one that is not that much tougher. But all of a sudden, this thing is not a function. Still a pretty simple equation, but not a function. What is it?
Circle.
Circle, center, 0, 0, and radius of 2. Okay, circles are not functions, right? Center at 0, 0, radius of 2. Now, there are two, actually, I guess probably two functions that are implicitly described by this interrelationship of letters and numbers. One is the upper half circle, semicircle. A semicircle, at least the upper half circle, that's not very good. Still not very good, but we'll live with that. What is the equation of that function? Well, we could solve for y. Let's do that. So y squared is 4 minus x squared. And y, take the square root of both sides, and when we do that, we have to account for both possibilities.
Plus or minus.
So let's go back. What is the equation of the upper half circle? The principal square root. So this equation is y equals the principal square root of 4 minus x squared. And that is a function, and it's solved in terms of x. We could take that derivative. I think we can get to the derivative quicker by using implicit differentiation, and we won't have to go through that process of solving for y in terms of x, deciding which is which. By the way, what would the equation of the lower semicircle be?
Negative.
The negative square root. So we have two functions implicitly described. Now don't use the right half circle, because that would not be a function, right? The left half circle would not be a function. So if we want to talk about functions, the upper semicircle, the lower semicircle. So we could take the derivative of that, and we have the ability to do that, and it's not like it's a ridiculous problem. But if we started with that, first of all, we'd have to solve for that. Then we'd have to find that derivative. What's the derivative of that semicircle y in terms of x?
1/2.
1/2?
1 over 4 minus.
4 minus x squared to what power?
Negative 1/2.
Times
2x.
derivative of what's inside. Well, the derivative of what's inside is negative 2x. So that's not like ridiculous, but we had to do some work to even get it to that point where we could find the derivative. So why don't we, instead of going through that process, this is a simple enough equation where it is, and let's find out what the derivative of y with respect to x is for any point on either half circle. So let's take things as they are. That's what you'll want to do in the implicit differentiation process and just derive them. If it's a product, use the product rule. If it's a quotient, use the quotient rule. This is a sum, so we'll just take the derivative of the first piece. What's the derivative of x squared with respect to x? 2x. I'm going to leave some space there in case somebody has a question that I'm anticipating. What's the derivative of the second thing with respect to x?
dy
2 dy.
dx.
Okay, now if the y is bothering you, here's what it is. It's something squared, right? What's the derivative of something squared? 2 times that same something, right? To the first times the derivative of that thing. Is that true?
Yep.
So we have something squared. It happens to be y. We'll fill that in a minute. Derivative of something squared is 2 times that thing to the first times the derivative of that thing. Well, what is that thing? It's y. So that's the chain rule. It's called implicit differentiation, but it's nothing more than the chain rule. Now, the question I'm anticipating is, why didn't we have that here? Well, you do. We just don't write it down. The thing inside is x, so it's 2 times x to the first times the derivative of what's inside. Well, what's inside? X. So we would be deriving x with respect to x. That's 1. So we typically don't do that when the variable's x. We better do it when it's y or t or q or r, because we're deriving with respect to x. And on the right side, we've got the derivative of 4, which is 0. Sorry, I know that's not doing well on that screen. Everybody okay with this equation? Let's get this to a point where we kind of have a solution. Dx over dx is just 1. All right, what would be next? Slide the 2x to the other side. And divide both sides by 2y. So dy over dx is what? Not a complicated derivative at all. If you know what the x value is of the point, plug it in, negate it in the numerator. If you know the y value of the point, plug it into the denominator. And we will pick up from this very point on Monday. Have a nice weekend.